Started. Well, welcome everyone to the seminar. So today's speaker is Avelino Vicente. Many of you will know him. Avelino got his PhD from Valencia University in 2011 under the supervision of José Valé and Martin Hirsch, and then went for a couple of postdocs in Würzburg, Orsay, Liège, and Valencia, and is now a Ramón y Cajal Fellow in Valencia, which is a tenure track position, which should end up in a permanent position there. So he's an expert in kind of neutrino physics and flavor physics in general, and contributed quite a bit to that field. And today he will be telling us about the inverse seesaw mechanism for neutrino masses. So please, Avelino, over to you.
Well, thank you, Michel, for the introduction, and thank you for having me. So it's a pleasure to at least see your faces and discuss with my colleagues virtually, even though it would be even nicer to visit Australia, something that I've never done before. So I really look forward to have the opportunity in the future. So it's a bit early in the morning for me, so I hope you don't find me a little bit sleepy. I'll try to wake up myself if I have to. So I'm going to discuss something that I guess most of you would be familiar with, which is neutrino masses. And I know that some of you are big experts on the subject. And in particular, I will concentrate on a mechanism that has been used for many years already, but it's not maybe as popular as the standard seesaw. And this will be the inverse seesaw. So let me see how this goes. First, I will give a very general introduction about the lepton sector and things that we know and things that we don't know. And I think this is going to be just to be on the same page and to maybe get everyone acquainted with the typical concept that we discuss in this field. Then I will concentrate on the inverse seesaw. I will give a theoretical review of the idea and some of the possible directions it can take. And then finally, in the second half or the last 40% of the seminar, I will discuss some phenomenological applications of the idea. And that will be my final message. I will try to convince you that this inverse seesaw leads to very interesting phenomenology in several ways. I will just give you two examples coming from works that I did recently, and I will conclude with some final remarks. Of course, let me say that you can interrupt me and ask questions any moment or afterwards, if you prefer. That will be fine for me, of course. So let me begin with the introduction. So, well, I think I don't need to convince you that we are living exciting times in particle physics. And I borrowed this graph from Patrick Koppenbuch, who's a member of LHCb. I guess most of you know him. This is a plot that basically compiles information about several observables that have been popular in the last years in flavor physics, most of them regarding leptons. And you can see that in some of them, the theoretical prediction would correspond to 0. So this, in the x-axis, you have the pool with respect to the standard model prediction. And you see that in some of them, there are some deviations which are already largest. The most famous one recently has been the Muon G-2 anomaly that is already above 4 sigma, if you believe in the theoretical calculations. That is also controversial. But there are several anomalies in flavor observables, such as RK, also RD and RD star, and P5 prime. So I think this is very interesting. And because of that, since now people are discussing that we might observe in these anomalies hints of standard model violation or physics beyond the standard model, I think it's important to ask again the question whether we have a good reason to go beyond the standard model. And the answer is obviously yes, because of neutrinos. So we know that there are things in the lepton sector that we don't understand, and they all have to do with neutrinos. So I guess you are familiar with this famous letter that Michel will be able to read much better than I will. This is a letter that Pauli sent to his colleagues when he couldn't attend a meeting that was held in Tübingen back in 1930. This meeting was about the main problems in particle physics and nuclear physics at the moment, and one of them was beta decay. They couldn't understand why the electron spectrum in beta decay was continuous and not just a single value, a particular value for the energy of the electron. And he proposed to solve this problem the existence of a new particle, the famous neutrino. this is a story that is very well known by everyone. I still find amusing that he was a bit embarrassed by doing this, because he was proposing a new particle that was never observed before, and that was something that he couldn't do openly. Like, he was a little bit embarrassed about it. And nowadays we propose tens of new particles in a single paper, and we are happy with that. So things have changed a lot since then. So that was the idea of the neutrino. And then very soon afterwards, Fermi took the idea and applied it to construct the first theory of beta decay, the famous Fermi theory. And in this effective theory, the neutrino appears. And actually, he also popularized the name, even though I read in some places that probably it wasn't him, it was Amaldi, but then Fermi was the one that made it popular, the name of neutrino. The application was very successful, as you know, with this theory. Even though it's very simple, you can explain many phenomena in beta decays and in weak decays in general, not only beta processes, but general weak decays. But still, this was still a theoretical idea. That eventually became reality when Cowan and Rains, about 20 years later, discovered neutrinos by running these experiments with nuclear reactors. They first thought about using a nuclear bomb, but then they thought better, and then they did it with a nuclear reactor. They had this huge amount of neutrinos coming from the nuclear reactor, and they used this clever idea of using the simultaneous presence of these photons coming from neutron capture and E plus E minus annihilation to detect neutrinos. This was the first of many, many successful neutrino experiments. And nowadays we have a lot of information about neutrinos. But back then, when basically the neutrino was discovered, and by accumulating more data, there was no clear hint of any neutrino mass. So the standard model was built under the assumption of massless neutrinos. So this was done by not introducing right-handed neutrinos in the theory, in contrast to the other fermions, which have left and right-handed components in the theory. Also, and this is very important, they didn't, the fathers of the standard model didn't include additional scalars or additional elements in the lepton sector, which is very minimal. And because of that, there is some accidental lepton number in the model. And well, this is a problem nowadays because we have several observations that already started in the 60s, 70s, when people started looking for neutrinos basically everywhere. For example, from the sun, the neutrinos are produced copiously in nuclear reactions in the sun. So you can just basically use solar models to calculate how many neutrinos will reach the Earth, and then how many of them will be detected by weather detectors. And by comparing this number to the number of neutrinos that are actually detected, see whether this understanding of the sun and of the neutrino actually matches the observation. And it was found immediately that the number of neutrinos were below the number of expected neutrinos. Similarly, if you look at neutrinos produced at the atmosphere, you see that the neutrinos do not follow the expectation. For instance, you would expect that for each electron neutrino, 2 muon neutrinos should be observed due to the number of neutrinos that you expect from the typical, from pion decay. And again, this was not observed. This was another problem. So where are the missing neutrinos? This was a question that people were asking themselves for many years, actually, for many years. And the answer is now very well known. There is a mechanism that is basically an application of quantum mechanics, which is called neutrinos oscillation. So when neutrinos are produced, they have a definite flavor, but then in their propagation, since the flavor and the mass basis do not match, they are different, they transform. And this makes some of the neutrinos to go to other flavors, and then when they are detected, they are not in the flavor they were expected to be. Because of that, they are not detected, and that explains the absence of these neutrinos in the final numbers. However, for this mechanism to work, neutrinos have to be massive. They need to have at least 2 of them, need to have non-zero masses. And this is already a proof that the standard model is incomplete. We need some addition of new fields, new symmetries, new mechanisms, new dynamics to explain how neutrinos get their masses. Now, but it's actually a bit more complicated than that. I did this very ugly looking plot by using some of the numbers that we have for the masses of the standard model particles. For the neutrinos, I basically used one electron volt just to give an estimate, even though we don't know this mass, and actually it will be lower than that. It's actually at the level of 0.1 electron volt at the moment, coming from cosmological observations. But anyway, I think the point is equally valid. You have here in log scale the masses of the different particles that we have discovered so far, from the Higgs boson to the charged leptons, and then below we have the neutrino, which, as I said, it has a mass which has to be below this line. So to me, it looks very interesting that there is a huge gap, and I'm using log scale, so the gap is actually really large between all the standard model particles and the neutrino. There seems to be something special about the neutrino. And this might be just a numerical value that, I don't know, randomly was selected at some point, or it could mean that maybe there is some additional physics behind this value that we should try to implement in our models when we try to explain neutrino masses. So we don't need only to explain neutrino masses, but also why these masses are so low in comparison to the rest of the particles in the standard model. And there is a solution that everybody knows, and it's the seesaw. So this was proposed already almost 50 years ago by Peter Minkowski, and then followed by many papers that basically rediscovered the idea. And it's actually very simple. You just extend the standard model with singlet fermions. You can call them right-handed neutrinos. And these guys are singlets under the standard model gauge symmetry. Because of that, you are allowed to write down a Majorana mass term for them. It doesn't break any symmetry, only lepton number, but that is not a gauge symmetry of the standard model. So in principle, you're allowed to do that. And when you do that, you end up with a matrix, a mass matrix for the neutrinos, left and right-handed neutrinos, which looks like this, where MR breaks a lepton number. And then if you assume that MD, so the Dirac mass term that is coming from the Yukawa coupling, is much lower than MR, so the right-handed neutrinos Majorana mass term, you get an approximate result for the neutrino mass term that looks like this. So it's proportional to the electroweak scale square divided by MR. So by assumption, if MR is very large, this will be naturally very small. This is the seesaw mechanism that everybody loves and likes, and it works perfectly. It is implemented very well in many unification theories, and it's perfectly fine. And actually, it comes in many varieties. So here you have the three versions of the seesaw that you can have at tree level. The type 1 seesaw is the one that I just discussed. It's the simplest of them with the singlet fermions. There is a very similar situation when you use triplet fermions instead, and you have it on the right, and you have some of your colleagues here in the list because they were the ones that proposed this idea. And there is also a version with a triplet scalar that is called type 2 seesaw. In all of them, the idea is basically the same. You have some very heavy particles, and the heaviness of these guys explains the lightness of neutrinos. So that's why this is called seesaw. And it works perfectly well, and there is no need for anything else, basically. However, it is also true that these models are boring what concerns phenomenology, because precisely due to the fact that these guys are so heavy, there are no way to produce them currently in current experiments, and maybe we will never be able to produce them because they are super heavy. And that's why people are looking at other directions, which are also interesting from the theoretical point of view, as interesting as the seesaw, but more interesting from the phenomenological point of view. And there are many models, many. So the ones that I explained are tree-level models, but some of the people in the audience are very familiar and experts on relative models, models in which neutrino masses are not produced at tree level, but at the one loop, two loop, or even higher loop orders. And some models, like the seesaw, for example, the classical seesaw, take place at high scale. So the new elements, the new ingredients lie at a very high scale. But there are also models with new elements at those scales, like the one that I will discuss now, later, the seesaw. Also, there are models that produce neutrino masses at dimension 5 based on the so-called Weinberg operator, a very famous contribution by by Weinberg. But there are also models that use higher dimensions, so dimension 7, dimension 9 operators. So there is a huge amount of models. I have never counted them, but I'm sure that in the hundreds. So it's like you have to take your favorite, or you have several favorites, and it's like PS. So basically, it's a matter of taste. There are arguments in favor of some models, arguments in favor of others. It's hard to just pick one. And it's just down to experiments to choose, of course. And you can basically classify them in two big families: models in which neutrinos are Dirac fermions and models in which neutrinos are Majorana fermions. The first case, Dirac fermions, is just a reproduction of what you do with the other fermions in the standard model. You just have a Dirac mass term, the simplest one, or not the simplest, maybe I should say simplest, but the most familiar type of fermion mass term, in which you involve left-handed and right-handed fermions. And this is, for example, what you have for the electron in Dirac's theory. This is one possibility, and the other one that was discovered by Majorana in the 30s is to use a property of Lorentz symmetry that allows you to write down a mass term for fermions just involving single chirality. This is called a Majorana mass term. You have here, you have it here on the right. And the only thing that you should know, well, you should know many things, but one of the things that you should know about this term is that in the way it is constructed, you can easily see that it violates U1 symmetries. All U1 symmetries will be violated by this term if F is carrying a charge under this symmetry. So, for example, if you want to conserve electric charge, you cannot use this type of mass term for the fermions with electric charge different from zero. But neutrinos are chargeless, so in principle, you can use them for neutrinos. These are the two types of neutrino mass models. I would say that the community favors Majorana fermions, Majorana neutrinos. There are several reasons for that. I think they are simpler to construct. Also, they are, as I said before, very well embedded in some unified theories. But Dirac fermions are equally as possible as Dirac neutrinos are equally valid. And I will discuss something about that later in my seminar. And let me conclude this introduction with some open questions that we have in the field. So we don't know the origin of neutrino masses. I think this is clear from my discussion. We don't know if they're Dirac or Majorana. Experimentally, we don't know what is the absolute scale of neutrino masses. We know they have to be lighter than some value, but we don't know their mass, their exact mass value. We don't know the ordering, whether 1, 2, 3 or 1, 3, 2, what is the ordering of different mass eigenstates. Also, we don't know if there are more than 3 neutrinos. Actually, there are several hints, several experiments that maybe could hint at the existence of additional neutrinos, but they have to be sterile if they exist, because we have measurements from set boson decays from Lepton that are conclusive about this. Now we have first hints of CP violation in the Lepton sector. I think this is something that is very eagerly awaited in the community. And finally, and this is one of the things that I discussed at the beginning of my seminar, we are now also maybe observing for the first time the violation of Lepton-Febvre universality with these observables RK, P5 prime, and so on, RD and RD star, for example, that I don't have time to discuss. I guess some of you will be very familiar with them. So as I said, very exciting topic. The Lepton sector has many mysteries, and it's actually very nice to be working on this field right now. I think this is very interesting. And with this, I conclude the introduction. I guess some of you will be looking like this at the moment. Sorry about that, if you were already familiar with this and it just repeated what you know. Let me move to the main subject of my seminar, so the inverse seesaw. The inverse seesaw is actually more than a model. You can call it a paradigm, and it's based on these two different ingredients. So the inverse seesaw is a mechanism for neutrino masses that uses a very small parameter that you typically can call it mu. So in all these models that I will discuss from now on, the inverse seesaw introduces a small parameter. And this small parameter has 4 ingredients that are very important. First of all, it has to be symmetry protected. This means that this parameter mu breaks a symmetry that I call here capital G down to another symmetry which is called here G prime, which can be 0. So it can be also no symmetry at all. And that implies also that when you take the limit mu going to 0, you increase the symmetry of the model. This is very important because then automatically all corrections to this parameter have to be proportional to the parameter itself due to symmetry protection. And therefore it is allowed to introduce this small parameter. You will see later how small it is compared to the other parameters in the model, without any problem with relative correction, for example. So this is very important. A second ingredient, it is typically taken to be dimensionful, so dimensions of mass. But there are variations in which you can have other positive dimensions, but always positive dimension, always positive dimension. Typically, as I say, dimension of mass. And the crucial ingredient is that neutrino masses will turn out to be proportional to some power of this mu parameter at leading order. And because of that, since we are assuming that the mu parameter is very small, neutrino masses will become small automatically due to this connection. And finally, I just wanted to make a comment about the possible existence of more than one mu parameter in general models. Typically, you take one, but there can be more than one. And the second big ingredient in the inverse seesaw is that you only allow for fermionic extensions of the standard model. So you only introduce additional fermions, you don't introduce additional scalars. With these ingredients, you can construct many models, and all of them, in my definition, well, my and my colleagues' definition, we call them inverse seesaw. Let me show you the original construction, and I think this will become easier to understand. So in the original construction for the inverse seesaw, you introduce two types of singlet fermions. You call them N and S. They are singlets under the standard model gauge symmetry. And because of that, you can introduce, for example, a Majorana mass term for the second of them, for S. Okay. You can also introduce a Dirac mass term that mixes M and S. And finally, M has a Yukawa coupling with the standard model leptons, a normal Yukawa coupling. So when the Higgs boson gets above, this guy here, the Yukawa coupling, induces a Dirac mass term, and you end up with a mass matrix like this. If you have three families of normal neutrinos, you need three of them at least, three families of N and three families of S. This matrix is 9 times 9, so it's a big matrix with this particular structure. And again, assuming that there is a particular hierarchy in between the different elements of the matrix, you end up with approximate expression for the neutrino mass matrix, which looks like this. And you see already the magic, it is proportional to mu. Since mu was very small by assumption in this construction, the Majorana mass term for the S singlet, there is a natural suppression for neutrino masses. And this is the magic of the inverse seesaw mechanism. Why is that important? You will see that is important because in that case, you don't need to introduce such large scales. So you don't need M, capital M here, to be that large. And therefore, the phenomenology in principle will be much richer than in the standard seesaw. This is the whole idea. By lowering the scale of new physics, lowering M, you end up with a richer phenomenology, and then you can test the mechanism in different experiments. Here you also have the Feynman diagram to understand how this process works. So mu is at the center of the diagram, and it is crucial for this to work. If mu is 0, neutrinos are massless, and you can check immediately that also if mu is 0, lepton number is conserved. Only when mu is different from 0, lepton number is broken in 2 units. So I just copied here the formula again. So this is the formula for neutrino masses that again, you can see it's proportional to mu, and you can play with numbers a little bit to see how small mu has to be. So if you assume that Y, the Yukawa couplings of order 1, the Yukawa couplings that are hidden in the Dirac mass term, and you want capital M, the scale of the right-handed neutrinos of the new singlets at the level of 1 TeV, in order to get neutrino masses at 1 electron volt, which is a typical scale of reference, you end up with the mu parameter here being of order 40 electron volts. So which is a very small quantity when you compare it to different scales in the model, for example, the electroweak scale or capital M. That's why in some people call this type of models a slightly broken lepton number, because this is the amount of lepton number breaking that you have allowed in your model. So it's a very, very small amount compared to other scales in the model. Let me insist once again on this idea of symmetry protection. If mu was exactly 0, then Lepton number would be conserved exactly. And because of that, mu, all the corrections to mu, will be proportional to itself. And therefore very small naturally. You don't have to do any fine-tuning or anything. And this is what back in the 80s Toft called naturality. So the fact that you can introduce small parameters, but they are fine because they are naturally protected. You don't need to introduce any fine-tuning in the model.
Avelino, can I ask a question on the make a comment as well?
Of course.
So this Lepton number is still anomalous number. It has anomaly. So that Hopf's condition doesn't apply strictly. In principle.
You are completely correct. I will show later constructions of this idea in which you can gauge Lepton number because it's anomaly free. But as it is here, it is anomalous. You are correct. Yes. Thanks for the comment. And of course, you are welcome to make ask as many comments as you want. I invite you to discuss and to interact with me. Okay, so I just said that this is natural, but I think we should also be aware that even though it's natural, we don't have an explanation for this number. So this is a very small number. And the smallness of this number can be understood in bigger theories. So there are constructions in which this is not explicit in the Lagrangian, so it's not a Bermas term in the Lagrangian, but you can generate it spontaneously. And in those cases, you can manage to explain the smallness of this parameter by playing with some large scale or some other ideas. You can also generate mu radiatively by playing with loops, and then also automatically this would be very small. So being technical doesn't tell you much about the origin. Technically natural, sorry, it doesn't tell you about its origin. It just tells you that it's fine, okay? But of course, it is okay to ask yourself what is the origin of this parameter in a bigger theory, and there are people working on that, and there are several papers, even though not many. I think this is an interesting line of research that maybe we should pursue more in the future. Okay, so to compare, so if the standard seesaw works thanks to the presence of a very heavy particle, in the case of the inverse seesaw, the crucial ingredient is a very small parameter, which is the mu parameter. So it works somehow the other way around. Now, let me go back to this original construction, but dress it a bit more. So now I will play with a spontaneous generation of mu parameter. And this connects to the comment that we just got. For example, we can play with B minus L, U1 B minus L, that as you know could be gauged if you have 3 families of right-handed neutrinos with Lepton number. And in this model that I'm proposing here, you start with the same ingredients we had before. So you have the standard model Lepton doublet, you have singlet fermions and an S, the standard model Higgs doublet, and you add also a singlet scalar chi, which will get above and will induce spontaneously the mu parameter. Okay, with these ingredients, and by assuming that the Lepton numbers of n and s are opposite. Okay, so let me highlight some of the main ingredients. By assuming that Lepton number of n is 1 and the Lepton number of s is -1, and also assuming that the Lepton number of chi is 2, you end up with this Lagrangian here. So you have new ingredients in the Lagrangian. You have a Yukawa coupling only with n, not with s, because of the choice of Lepton number. You can write down a Dirac mass term between n and s, and you can write down 2 additional Yukawa couplings using chi. So these Yukawa couplings, when chi gets above, will induce a mu parameter here. Okay, so mu will be basically lambda times the wave of chi that I call you here. And you will induce an additional or extra mu parameter, I call it here mu prime, that actually will lead to a math matrix. You have it here below with an additional entry here in the 2x2 element. This additional entry actually is numerically irrelevant. You can show by using perturbation theory that it enters neutrino masses, of course, but it enters subdominant compared to mu because of this 0 here. This is the crucial point. Because you have a 0, mu prime enters subdominantly thanks to, and then you can basically neglect it in your calculation of neutrino masses, but it is there in principle, and you cannot forbid it because the Lepton number symmetry that you have used to construct this theory cannot be used to forbid this term if you don't forbid this term as well. So the construction doesn't allow you to have this and not the other. And this is something that will happen, as you will see, in all the models that I will discuss in this seminar, that you always have additional mu parameters, but they are numerically irrelevant. Again, the model works exactly as the one I discussed before, but with the difference that now the mu parameter is not explicit, but is spontaneously generated when chi gets above. But the symmetry, the fact that the symmetry is spontaneously broken, Lepton number, doesn't make any difference in what concerns the expression for neutrino masses. So you get this expression plus subleading terms, and in these subleading terms you have mu prime, mu, and many combinations and additional powers of mu and mu prime. So this is just a possible way to dress the inverse seesaw with an additional scalar, with a possible origin for the symmetry. Sorry, not for the symmetry, but for the structure of the mass matrix. Why you have a zero, for example, here? It's coming from the fact that you have U1 Lepton number or U1 B minus L working below symmetry breaking, and this is what gives you this zero. But there are many variants in which you can construct this idea, or you get this idea from higher or larger constructions. I will discuss briefly, because I don't want to bother you with many details, possible variants of this idea. And there are three possible directions you can take. For example, you can use higher multiplets. I'm using in these simple examples singlets, but you can use, as you will see, other multiplets. You can construct what people call multiple inverse seesaw. You will see some examples. In this case, you don't get neutrino masses proportional to mu, but to mu to some power. So power 2, 3, etc. And you can use also the inverse seesaw for Dirac neutrinos. And I will try to explain this in a while. The first thing that is very simple to understand is that you can use higher multiplets. And I'm just using the standard diagram for the inverse seesaw with some possible fields running inside the fermion lines or in the scalar lines which are external. This phi here could be the standard model Higgs or could be different, and therefore their quantum numbers, or its quantum numbers, can be in principle different from the standard model Higgs quantum numbers. And this scalar here in principle also has many possibilities. If these numbers here are defined as n, y, and 0, so n under AC2L, y under U1 Ibert charge, of course, and then 0 under Lepton number, then all the other fermions here have to have these numbers here in order for this diagram to be invariant under all the symmetries. And you can see that in principle you have many possibilities. The simplest one is the one that I explained before. So n equal 2, and then here you can take n minus 1, so you get singlets in the fermion line. Also y equal 1/2, then because this is the hypercharge of the standard model Higgs doublet. Also here you have some choices, but once you have fixed this and fixed this is fixed as well. And you can in principle construct many variants. Here you have a table with some examples. The one that I just explained and that I illustrated before just takes this choice 2, 1, 0. But you can play with all the possibilities. For example, you can play with triplet fermions in the internal line. And this is something that I will explain later in an example, but you know this works because this is exactly the same idea that you have in the type 3 seesaw. So you can construct a type 3 inverse seesaw exactly in the same way. And you have more exotic variants. For example, you can use scalars which are not the Higgs doublet in the external lines. And then, for example, you can have a 4-plet. And this introduces also the possibility of having triplets and 5-plets for the fermions and for the additional scalar. So you can construct many possibilities. This has been studied a lot. And basically the final formula for neutrino masses is exactly the same. But of course, as you can expect, the phenomenology changes a lot. Another direction that you can take is the multiple inverse seesaw direction. And here I have an example with a double inverse seesaw. So now you have basically the same fields, the same symmetry, B minus L, but in addition of M and S, I have replaced M by a vector-like fermion. So now M has a left-handed and a right-handed component, and they both have the same charges under all symmetries. And S has 0 B minus L charge. Okay, I have modified also the charge of S. When you do this, you end up with these additional terms in the Lagrangian. Again, you have some Dirac masses. In this case, a Dirac mass, sorry, not Dirac. This is Dirac, but this is Majorana. So you have a Dirac mass for the vector-like fermion and a Majorana mass for this additional fermion. This is allowed because this is it has a vanishing charge under B minus L, of course, under all the symmetries in the standard model. And you have these additional Yukawa couplings. Again, when chi gets above, you end up with a mu parameter, and actually you end up also with an extra mu prime parameter. And this is the structure of the mass matrix that is now larger because you have additional fermions. And as usual, you work under the assumption of some hierarchy between the different couplings or between the different scales in the model. If mu and mu prime are much smaller than MD, and these are much smaller than MM and MS, this is the formula that you get for neutrino masses. And now, instead of being proportional to mu, it's proportional to mu squared. That's why people call this the double inverse seesaw mechanism. And you can also understand it diagrammatically, as you can see here. And you can construct versions of this idea with a triple inverse seesaw, quadruple inverse seesaw, and so on. Why is this attractive? Because the larger the power of the mu parameter in the formula, the less suppressed you need it to be to get neutrino masses at low scales. And finally, let me comment on a possible Dirac version. In this case, we have to add right-handed neutrinos, so new R, because we have to construct a Dirac mass term for neutrinos. And we have constructed this model in this particular way. It's a bit more complicated. For example, now the B minus L charge has to be given for the right-handed neutrinos in a non-universal way, -4, -4, 5. This is a very well-known solution to get anomaly-free B minus L symmetry that has been around in the market for several years already. We didn't discover this. And you need additional fermions. That's why the Dirac version is a bit more complicated. And also additional scalars. We have chi1 and chi2. I don't want to explain this in more detail than this. Basically, you end up with a bunch of additional terms in the scalar Lagrangian, and also, of course, in the Yukawa Lagrangian. The Dirac mass term for the extended lepton sector looks like this, with a Dirac mass matrix with this particular structure. And then again, assuming that there is a hierarchy between the scales in the model, you end up with an expression for the now Dirac mass matrix for the neutrinos, which is proportional to mu1 and mu2. So again, if mu1 and mu2 are both small, which is the assumption behind this calculation, you naturally get small neutrino masses, and in this case, Dirac neutrino masses. In fact, this is a double Dirac inverse seesaw, as you can see. It's proportional to two mu parameters, and you can construct a very similar model with just one. I didn't explain it here because it's a bit confusing, because it looks exactly as the Dirac seesaw, but it is also a possibility, and I just wanted to mention this. This is just to say that the idea of inverse seesaw or inverse seesaw in general beyond the Majorana construction in principle can be used in exactly the same way. Now, since I'm a bit late, I wanted to conclude a bit earlier the previous discussion. Let me be a bit faster in the last part because I don't want you to be bored. Let me just comment on some possible phenomenological directions. As you can imagine, if these additional mediators of the seesaw are lighter than usual, so if they are around the TB scale, there are many signatures you can look for. For example, you can produce them at the LHC if you are lucky and they have large Yukawa couplings or they are charged under the gate symmetry. You can also have them in flavor observations. You can find them running in the loops that produce, for example, Lepton flavor violation. You can get contributions also to some flavor conserving observables like the Muon G-2 that is very popular now. So let me just comment on two possibilities to convince you that actually the inverse seesaw is a very rich scenario for phenomenology. And the first one that I wanted to mention is Lepton flavor violation. So let me just make a few comments before going to the inverse seesaw. You know that, well, the observation of flavor violation with charged leptons, and this is why I have a C here, would be a very clear sign of non-trivial physics beyond the standard model. But in fact, most of the models that go beyond the standard model predict very large, even by default, totally forbidden rates for Lepton flavor violation. And this is just because they typically, the new ingredients that you have in these BSM models, they produce these operators. And unless you have some mechanism to suppress them, they are typically very large, very large. The coefficients of these operators are very large. For example, if you have a 4 fermion operator of this type, so this is a very simple 4 fermion operator with muons and electrons that violates both the muon flavor and the electron flavor, this coefficient in front of the operator, that is of dimension 5, has to dimension 6, sorry, has to be larger than about 100 TeV. So you see that typically the constraints that we have for these Lepton flavor rates are so strong that you get constraints on these coefficients that are actually larger than the collider energies that we are handling at the moment, for example, at the LHC. And there are several experimental projects going on at the moment, and they have been evolving with time since the very beginning. So since the discovery of the muon, basically, people are looking for these flavor violating decays. And after decades of evolution, we are now basically here. There are several experiments with very high sensitivities. I took this plot from this paper. It's a bit old, but I think the numbers didn't change that much. So I think it's still valid. And the experimental effort is actually basically a worldwide effort. There are experiments in several nodes. For example, in Europe, you have MEG and Mu2 as specialized experiments looking for flavor violation. Also the LHC, because in principle you can also use LHCb and also the high energy collisions to look for flavor violation. And in the US, you have this project Mu2, which is looking for Mu2 conversion, muon to electron conversion in nuclei. And in Japan, you have several experiments also looking for muon to electron conversion in nuclei, like DIM, COMET, and the future. This is a bit in the future, Prism Prime. And BEL2, which is already running, that is also potentially capable of finding Lepton flavor violation. However, in some models, this is also something that we have to remember, you expect unobservable Lepton flavor violation. For example, in the case of Dirac neutrino masses, the simplest model for neutrino masses, just extending the standard model in the same way as for the other fermions, you end up with this prediction that is super famous. So once you have neutrino masses, the charge current interaction gets modified, and you get a new matrix here exactly as in the quartz sector. So in the quartz sector, you would have the CKM matrix. In the lepton sector, this is usually called the PMNS matrix. And all charge current interactions have to have this coupling here with the PMNS matrix elements appearing in the calculation. And because of that, if you calculate, for example, some lepton alpha going to lepton beta gamma, you get an expression that has to be proportional to 2 powers of this, well, 2 elements of this matrix. And it looks something like this. And the point is that since this matrix is unitary, in the limit in which neutrino masses are 0, these observables, these rates have to be exactly 0 due to the Jim mechanism. It's nothing but the Jim mechanism. Because of that, all the rates have to be suppressed by neutrino masses. And in fact, they are suppressed by 4 powers of neutrino masses. And this basically tells you that this has to be very suppressed. So this is the expectation in these very simple models. But the nice thing is that when you go to the inverse seesaw, and this was discovered many years ago in several papers. The first one I know about is from 1995 from Ilakovac and Pilatsis. In the presence of sterile fermions, since they don't couple directly to the W, but they have to couple only through mixing with the left-handed neutrinos, this suppression gets spoiled. So you end up with large penguins in the inverse seesaw due to the presence of these additional fermions. And in principle, you can reach rates as large as the current limit, for example, in Mu3 gamma. So this is one of the first comments that I wanted to make. But more recently, in several papers, people realized that the same thing happens in other types of diagrams. For example, this would be a box diagram contributing to Mu3 conversion in nuclei. but also if you replace quarks by leptons, it would be also valid for mu2 electrons, for example. You have here electrons in this line and neutrinos here. So these boxes can also be very large. And actually, this is very interesting when this was discovered, when the light singlets, which are here, are very light, light meaning a few giga electron volts or around, not larger than the TV, of course. And this is important because these contributions are independent of the penguins that I explained before. So these are non-dipole, and therefore the phenomenology gets richer. You have independent contributions. So back in 2014, this is a bit old, but I think it's still completely valid. We did a work in this direction. We wanted to see whether these contributions in a full numerical scan with all the possible diagrams actually render the model richer than expected or just boring. And in order to see that, we did an analytical and numerical study of these observables. So lepton to lepton gamma, lepton to 3 leptons with all possible combinations, and finally mu2 conversion in nuclei. We considered these observables. We calculated all possible contributions. That means a few hundred Feynman diagrams. We had to use a code for that. We call it flavor kit. And thanks to that, we were able to study this in detail. And let me just show you a couple of examples to convince you that this is interesting, and I will finish this part. So the first result that I wanted to show is this lepton to lepton gamma. Actually, this shouldn't be here because actually you have here other observables, so sorry about that. Here you have some rates for some observables as a function of the mass of the additional fermions. And you can see for some particular values of the other parameters, I think they are not very important. You can see that when the additional fermions, which have masses proportional to this M, are light, so a few hundred GeV, 100 GeV, 200 GeV, and so on, all the rates can have similar sizes. And actually, they would be excluded here because the current limit on, for example, mu2 gamma is at the level of 10 to the minus 13. Okay, 4 times 10 to the minus 13. So over here. Okay, so everything below this line would be excluded. But the main point that I wanted to make with this plot is that they can have similar rates. What that means is that they are not proportional to the same operator, because when they are proportional to the same operator, you expect a situation like this here. You expect mu2 gamma to be much larger than the others because it is less suppressed. All the others have additional Yukawa insertions, or to be more precise, mass insertions, okay? And also alpha insertions. So the electromagnetic coupling appears in higher powers. So this is just to show you that you can get large lepton violating rates, and also that this dipole dominance that actually takes place here can be broken at low energies, not low, but 100 GeV. And this actually is very interesting because you can see all the observables together. You don't need to observe only one, as in many cases. And actually, we did this calculation in supersymmetry. I mean, we were a bit masochistic because we wanted to calculate all the possible contributions to this observable, also supersymmetric ones. And then, as you can see here, I'm plotting this branching ratio as a function of capital M that you know already, and also as a function of the supersymmetric mass scale. And you see that, well, the full line corresponds to the total branching ratio, in both diagrams, in both plots, and the different dashed lines correspond to the different contributions that you have, for example, from photon penguins, set penguins, supersymmetric and non-supersymmetric boxes. And the main message that I want you to have from this plot, from these plots, is that the phenomenology is very rich. Depending on these two mass scales, you can have less, for example, SUSY boxes or non-SUSY boxes, and basically it's a mess, but it also means that the parameter space is very rich, and you can have all possible of hierarchies between the different observables. Okay, I conclude this discussion about lepton violation. So if you have any comment or question, it's a good moment. If not, we can also discuss later, as you prefer. And in the last 5 minutes, let me comment briefly on this possibility of explaining also the G-2 of the muon, the anomaly that we have maybe observed recently with the inverse seesaw. Well, I think you know about this. I don't need to explain this in much detail. This is the current, the latest measurement by the Muon G-2 collaboration at Fermilab, that more or less matches the previous observation by the Brookhaven experiment. And they basically give you this experimental average, which is about 4.2 sigma away from the standard model prediction that is, let's say, the official prediction. Some people don't agree with this, and they think that the standard model prediction should be closer to the experimental average. Nevertheless, this has been a very popular subject in the community in the last months. And one observation that I wanted to start with is that this cannot be explained in normal seesaw models. And this is something that Carla Biggio pointed out in 2008, and it's very easy to understand. First of all, in all standard seesaws, the only charged leptons that intervene are left-handed, purely left-handed. Because of that, in any diagram that you draw for the Muon G-2, you always need some mass insertion to get the chirality flip. So you will always pay, in this case, a Muon mass suppression in the calculation of the G-2. There is no way out of that in the standard seesaw. So the only chirality flip that you can have is the Muon mass, nothing else. So this is the first observation. But more importantly, you can also see, and well, this is a technical thing, I cannot give you an argument, that you always get a negative prediction. So the contribution from the standard seesaw, which is given here, is always negative. So, and this is even more important. So it's very small because of the chirality flip that you need due to the Muon mass, but also it goes in the wrong direction. It will make delta AL, delta mu in this case, to go negative instead of positive, as you need to explain the anomaly. So this applies also to inverse seesaw setup. There is no way out. It applies to type 1, type 2, and type 3 seesaws. It applies basically to all minimal seesaws. There is no way out. And even if you can fix the sign, which you cannot, okay, you have tiny contributions because the parameters that enter here, for example, the Dirac mass and so on, are suppressed due to constraints, for example, from the non-observation of non-unitarity in Lepton processes. So you need to extend a little bit the inverse seesaw if you want to explain the G-2 of the Muon. And in this paper, we did this. So we constructed a type 3 inverse seesaw. So instead of additional singlet fermions, we have additional triplet fermions. We call them sigma and sigma prime. And in addition, because we need additional ingredients to explain the G-2 of the Muon, we had these vector-like leptons. And this is crucial. Why is it crucial? Because this will provide the chirality flip that you need to increase the contribution to the G-2 of the Muon. And also you should know that these vector-like fermions, vector-like leptons, which are taken as doublets of the standard model gauge symmetry, actually have a mixing with the triplets, with the elements of the triplets after symmetry breaking due to this Yukawa coupling here. So this is how the triplets look like. You can write them in this standard notation. And then after symmetry breaking, as I said, they mix with the elements in the vector-like leptons, and also, as usual in the type 3 seesaw, they mix with the elements in the lepton doublet, in the standard model lepton doublet. So you end up with large mass matrices, as you can see here. This is for the neutral fermions, this is for the charged fermions. And assuming, again, the standard hierarchy in the inverse seesaw, you end up with this result for the neutrino mass matrix, which is the standard result that you know already, proportional to mu. So this is just the inverse seesaw. And for the charged leptons, you end up with the charged lepton mass matrix being proportional to ME, so to this element here, which is nothing but the standard model expression, plus some subleading corrections, which have to do, of course, with the mixing. But they are subleading and numerically irrelevant. I cannot convince you, you need to do numbers to see that, but believe me, they are subleading numerically. However, they are not subleading in the phenomenology. They are very important because these mixings actually play a big role in explaining how you get this contribution from the inverse seesaw, in the G-2. So now you get something like this. The diagram, instead of having here the singlets, now you have the triplets. So it basically looks the same, but thanks to the presence of these additional vector-like leptons, you enter these guys here, and because of that, you end up having the chirality flip, not by the standard model Muon mass, but by this additional Yukawa coupling, which is not that suppressed. Also, the sign is free. You don't get a prediction for the sign, and then you can adjust it to get a positive sign. All in all, and now I will show you a plot, and I will conclude with that, you can explain the G-2 of the muon more or less easily. So this is the plot that I wanted to tell you. You see that in principle, if you plot this particular, so this observable, the contribution to delta mu as a function of this particular combination that enters the diagram. Actually, this combination, you can read it off from the diagram here. So you basically find it here just by looking at this diagram. You see that this correlates very well as expected. This is the dominant diagram contributing to this observable. Even though in our calculation we included all of them, we actually see that this is the diagram. That's why I highlighted the presence of this diagram, because it helps you understand the main ingredients. And in this plot, you see the blue dots, which respect all the possible constraints, and the gray dots, which violate some constraints. For example, they lead to set to mu different from the observed rates, or they have problems with electroweak data or with LHC searches. So you see that in principle, it's very easy to get a large delta mu, but when you introduce the constraints, well, it's not that simple, okay? So you can explain the observation at 1 sigma, but you don't get many points in this region. At 3 sigma, it's easy, okay? You get many, but at 1 sigma, it's not that trivial anymore. But in principle, it works. So these are just 2 examples that I wanted to show you, but I hope I convince you that the inverse seesaw is very simple, but yet also a very powerful mechanism for neutrino masses that can be implemented in many different ways. Typically, people think about the Majorana inverse seesaw, but you can also do a Dirac inverse seesaw or a double inverse seesaw. I showed you some examples, but there are many in the literature. And finally, with these 2 examples about Lepton violation and G-2, I hope I convince you that the phenomenology is very rich. These are just 2 examples, the ones I'm more familiar with. That's why I selected them. But people have studied also LHC searches and many other things. Thank you very much for your attention. I hope I didn't stand very much in time. And now, of course, I would like to hear your opinion and get your questions and comments. Thank you.
Yeah, thank you very much, Avelino. Very nice talk. So we have time for questions. Who would like to go first? Maybe let me start.
Sure.
Can you go back to slide 49?
Sure. Here. Yeah.
Yeah. So on that busy slide, or busy plot. So when I look at it, so one thing what I noticed is that if you go to low masses, then typically the non-SUSY contributions become more important
yes,
compared to the SUSY. Is there a reason for that?
So I didn't explain this well because it wasn't the point. I just wanted to highlight that the phenomenology can be very rich. So let me now explain a little bit. So the plot on the left is done with Barayin M, so with Barayin, let's say, singlet mass, but with a fixed value of M SUSY. So the SUSY supersymmetric masses here are fixed in this plot, and they are about 1 TeV. So that's why here in this region, when you are on the left of the plot, all supersymmetric guys are much heavier than the singlet fermions.
Okay. Makes sense.
And also here on the right-hand side, you have Barayin supersymmetric masses, but fixed stellar neutrino mass. So the singlet fermions have 1 TeV masses in this plot. So that's why when you go to very low supersymmetric masses, well, you have to go to forbidden regions, but okay, you see at least qualitatively that some supersymmetric contributions, for example, the SUSY penguins, can actually be dominant when you go to this region. So it's just because they are lighter. There is nothing else.
Okay. So no, thanks.
Our point here was that all contributions could be important in some regions of parameter space. And then the typical expectation that you have in supersymmetric models or in seesaw models, that this is the dominant contribution always, doesn't hold anymore. Okay, so anything can happen.
Very good. Thanks. Are there other questions?
Maybe a last question. Yeah, of course, maybe this is a very model dependent thing, but do you think any of so-called smoking gun signatures with which you can say that yeah, it's definitely inverse seesaw which realized.
Thank you. Very, very good question. Actually, there is one thing that I didn't comment. Maybe it was a little bit quick. That would be the smoking gun you're looking for. So due to the fact, let me go back a little bit and then maybe. Okay, well, I don't have formulas so to support this, but when you calculate the eigenvalues of this matrix for the light neutrinos, you get this formula here, the inverse seesaw formula that you have seen 1,000 times in my talk. But you can also calculate what are the masses of the heavy fermions. And the masses of the heavy fermions are basically capital M. This is what I said already many times, but it's not exactly capital M. You have pseudo Dirac plus. So you get a guy that is capital M plus mu, and the other one is capital M minus mu. So this pseudo Dirac plus is a very clear signature, a very clear prediction in the inverse seesaw. And it has to do with the fact that you are violating Lepton number by a very small amount. They would be exactly Dirac if Lepton number is conserved. So the problem is that, of course, you have to discover these guys first, and then you have to measure their masses very precisely to see that they are actually not mass degenerate. You need a little bit of a difference, and the difference could be of a few kilo electron volts. So it's not simple. But that would be, in my opinion, the clearest signal of something like this going on. All the other things you can get in other models. You can get Lepton violation, you can get G-2, of course. So there is nothing special about them.
Thank you. So you need to discover this heavy fermion and then do careful spectroscopy of those.
Yes. That's. I think that would be the clear smoking gun. And thank you for the question. That was right to the point. Thanks.
Would there be some sort of transition from one to the other involving a very soft photon?
Indeed. That would be also that would be a consequence of this. But I don't know how easy or hard it is to see that experimentally. But yes, you are correct.
It would have to be boosted to give any chance of seeing it. That would seem to be quite difficult. Yes.
Also, let me also point out that I was concentrating here on the, let's say, the most ambitious scenario in which mu is very, very small. Okay, of the order of a few electron volts or kilo electron volt at most. But if you increase a little bit mu, if you make it maybe mega electron volt, then of course you have to reduce the Yukawa couplings. You lose all the other signatures because lepton violation G-2 goes down. But you increase the difference in mass between the two guys, the two pseudo Dirac guys, and then all these other signatures we are discussing now could be in principle more easily visible. So yes, all this is a possibility. All these possibilities do exist, and I think there would be very clear signatures of some inverse seesaw-like scenario behind. Thank you. Yes.
Thanks.
I would have a question. Thanks for the talk, first of all. So we're talking a lot about lepton flavor physics that you can do with inverse seesaw. I was wondering, is like other fields in theoretical physics, could it also be useful for, like, especially, I guess, dark matter maybe? Because you always have like extended symmetry that then is broken down to Z2 or something. I don't know. Are you aware of connections to dark matter physics, or maybe also, I don't know, Higgs vacuum physics or so?
Also, excellent question. So yes, you are completely right. So I realized that I was a little bit late when I finished the introduction. That's why I didn't explain some of the details that appear in this slide. And in fact, you are very correct. So when you break B-L in all these models that I have discussed in this section, you end up with some remnant symmetry. In the case of Majorana neutrinos, this is a set 2. You can call it some lepton parity. So leptons are odd, and it's nothing but angular momentum conservation. There is nothing special about it. But for example, in the case of the Dirac seesaw, the symmetry is set 3. This is actually what forbids the Majorana masses for the neutrinos, and that's why you end up with a Dirac neutrino, not a Majorana neutrino, because a Majorana term would break this set 3. So in principle, if you arrange your particle content in these constructions in such a way that you have a valid dark matter candidate that is charged under this remnant symmetry, you can combine both things and you end up with a valid dark matter candidate, and people have done that already. So yes, It's a very good idea and it works. And the other comment you made was about, sorry, so you said stability of the scalar potential and the Higgs. Yes. I'm not sure about the inverse seesaw being used in this direction. Probably yes, but I know some of my colleagues here in Valencia have discussed how in seesaw models, since you typically need, if you want the seesaw to be spontaneous, so if Lepton number takes place spontaneously, you need additional scalars. These additional scalars, of course, influence the scalar potential for the Higgs and typically help you having a better stability prospects for the Higgs. So I'm not sure it has been shown explicitly for the inverse seesaw, but I think it would be exactly the same.
Okay.
And maybe it has been, I just don't remember. So probably yes.
Okay, thank you.
Thank you.
Yeah, thank you very much, Avelino. I think we finished the official part.